I hope you're doing well. We will continue our discussion of Mathematical Statistics 1 by talking about the multivariate probability distribution. So this is chapter 5 of the textbook. Okay, so we begin our discussion with the notion of a bivariate discrete random variable. So let x be a pair of random variable, x1, x2, where each of the x1 and x2 are both discrete random variables. We will then refer to x, the pair x, to be a discrete bivariate random variable. So for example, if x1 belongs to the set S, which is discrete, and x2 belongs to the set T, which is also discrete, then x1, x2 will belong to the set S Cartesian product with T, which is also going to be discrete. That's why x is referred to as a discrete bivariate. Associated to x is a notion of a joint PMF, which is written in notation as this little script p, where p x1, x2 is nothing more than the probability that x1 equal to x1 and x2 equal to x2. So we note a few trivial but useful property to know in any case is that p is non-negative, so the PMF is non-negative. The sum of the PMF will be equal to 1. And finally, for any subset A in R square, in general speaking, we will always assume that because S belongs to R and T is a set of R, that S Cartesian product with T is a subset of R square. In general, we will never talk about, never really specified S and T, well, never may be the wrong word. We may, on occasion, not specify S and T, so that is why we will talk about A subset of R square. In that case, the property of the set A, the probability of the set A, which is the summation of the PMF, but we have to be careful about summing over a countable versus uncountable number of arguments, so therefore we will require the sum to be summation over the set for which the PMF is bigger than 0. So this set is a countable or discrete set. Just to avoid the issue of countable versus uncountable summation. So as a quick example, suppose we roll a fair dice twice, x1, x2 be the faces shown on the first and second row. Then we can think of x here, which is this bivariate random variable, to take on 36 possible values, namely the 6 values for the first phase multiplied with the 6 value for the second phase. And because the die is fair, we can assume that the PMF is equivalently 1 over 36. All combinations equally likely. As another example, now we toss a fair coin 6 times and we let x1 and x2 be the number of heads and the number of tails. So we note that x1 plus x2 obviously has to be equal to 6. So if we let x be this bivariate random variable, then due to the condition that x1 plus x2 equal to 6, we see that the set of the value of x are the 7 values from 0, 6 all the way up to 6, 0. And so because x1 and x2 uniquely, each of the x1 and x2 uniquely determine the p, so p x1, x2 is simply this one, which is just the PMF for a binomial with 6 trial and success probability 1/2. So we will now next introduce the notion of the joint cumulative distribution function. And so for any bivariate random variable, x, which is x1, x2, we can define the joint CDF for x to be simply the probability that x1 is less than little x1 and x2 is less than little x2, where now x1 and x2 could be any value in R square, R times R. So here we use argument x for the short notation little x here, because we don't want to write f of little x1, little x2. In any case, when x is bivariate and discrete, then the joint CDF is simply written as the sum of the PMF, sum of PMF. And here, once again, the summation is over all y with positive probability. So we write y less than or equal to x if and only if y1 less than or equal to x1 and y2 less than or equal to x2 as a shorthand notation. So for example, let's go back to our fair die once more. If we look at 2, and 4, then the property that the fair die, the two rows x1, x2, is less than little x1, little x2, in this case 2 and 4, is just given by the first x1 could take on either the value 1 or 2, and then the value x2 could take on the either value 1, 2, or 3, or 4. So total, we have 8 over 36. Meanwhile, for the case of tossing a fair coin 6 times, and if we let little x be 3 or 5, then basically capital X1 less than little x1 and capital X2 less than little x2 includes just the possibility at 1 and 5, 2 and 4, and 3 and 3. Because, for example, 0, 6 is not less than 3, 5. Because 6 is not less than 5. So in this case, the probability is now 41 over 64. So the joint CDF, we recall that for the univariate CDF, we have that f of negative infinity is equal to 0, f infinity is equal to 1, and f is increasing. So what that meant is that fx less than or equal to fy if x less than or equal to y. So in the case of the joint CDF, it is now, instead of increasing, it's monotone increasing in each argument. So more specifically, we have f for negative infinity and negative infinity is the same as f for any value x1 and negative infinity is the same as f of negative infinity x2 for any value of x2, both of which is equal to 0, just because the probability that x2 less than or equal to negative infinity is always equal to 0, irrespective of x1. And vice versa. And then furthermore, f infinity equal to 1. The third condition here, which looks a little bit surprising, strange, due to these four symbols, x1 star, x2 star, x1, x2 star, and so on and so forth, this here is nothing more than the probability that x1 less than little capital X1 less than x1 star, and x2 less than equal to x2 less than x2 star. So please verify this. So this is what we meant by this condition. And so that is why it is bigger than or equal to 0. Okay, so we will now next define the notion of the bivariate continuous random variable. So the first part of these lectures are usually only describing the definition and maybe some commentary about the definition. You can take a look at the book for examples. Generally speaking, most of the examples in the book or in any book on this kind of topics are a little bit, say, artificial or contrived. And that's just because they just try to illustrate the definition. So I don't think the examples are particularly interesting. So that's why we will skip most of the example. You can take a look at the book for the details. Okay, in any case, because the univariate continuous random variable is defined using a univariate integral, Therefore, a bivariate continuous random variable is then defined in terms of a bivariate integral. So, I guess analogously. So the definition goes as follows. We now have two random variables, x1 and x2. Bivariate, like we said. Then they are set, and they suppose that they will have a joint CDF, which you denote by capital F. Then this bivariate random variable x is set to be a bivariate continuous random variable if the joint CDF can be written as an integral. So the joint CDF can be written as an integral. And we require this to hold for all x1 and x2. So in any case, for any value of x1 and for any value of x2, the joint CDF is written as a bivariate integral in x1 and x2. Well, if you're really a little bit precise, you may say, well, the way we write it here is not exactly, is maybe like sloppy notation-wise. We should say this to be d of, say, like, maybe, let's fix this typo here. Let's call this d of, say, like w, and this is z, and then this becomes dz, and this becomes dw. So just to avoid using the x1 and x2 in the integration. So let's replace it like this. Okay, in any case, the function f with the above property will be referred to as a joint PDF. And the key word here is a. So if you remember in chapter 4, we talked about there is no unique PDF in the case of a univariate continuous random variable. Similarly, there is no unique joint PDF. So any function f with this property, which is this property here, will be one candidate. And usually we will have a canonical candidate. So the canonical candidate is defined simply as partial over x1 and partial x1, partial x2 of the partial derivative of the CDF, of the joint CDF. But that's not really important for us as of this point. Okay, so the key point here, and one thing that I wanted to emphasize very carefully, is that similar to the case of the univariate continuous random variable, the probability that capital X equal to little x is always 0. So we will never really observe any single value. We observe a value in a neighborhood, but we never really observe any single value. The integration obviously have to be equal to 1 of the PDF, joint PDF. And now the key point now is that for any set A, that can be written as a union of rectangles. So for example, if we can write A as, say, like A1, B1 multiplied by, say, like C1, D1 for the first rectangle, union, say, A2, B2 multiplied by C2, D2 for the second rectangle, union dot dot dot. So we think of A1, B1, this rectangle here, this is A1, and this is B1, and then we have then C1, D1, C1, let's say that, let's fix this to be like C1 and then D1. Then we can think of this as the rectangle covered by this region here. So if A is a union or intersection of rectangles, then the probability that X belong to random variable A is simply obtained by integrating the joint PDF over the region defined by A. So as we say earlier, you cannot define probability that X belong to A for all sets A. This is not definable, cannot define. So we have to limit ourselves to countable union of rectangles. So that's just a technicality. So in any case, let's see a quick example here. So this is example 5.4 in your textbook. So the question goes a little bit long, but you have gasoline in the bulk tank. You have Y1, which is the proportion of the bulk tank available after the tank is stocked. And then Y2 be the proportion of the capacity of the bulk tank sold during the week. Then, because they are proportions, they take on the value between 0 and 1, because the further amount the amount sold cannot exceed the amount available. So Y2, the amount sold, cannot exceed the amount available. So this is a contrived example. So suppose that the joint density, the joint PDF, is given here, and you want to find the probability that that less than half of the tank will be stocked. So Y1 less than 0.5, and more than 1/4 of the tank will be sold. So Y2 is bigger than 0.25. So now the only thing that is interesting about this problem, a contrived problem nevertheless, is that you want to integrate over the region. But the PDF here is only defined inside this triangle. So suppose the triangle is, say, from 0 to 1, Y1, 0 to 1. And this is the line Y2 equal to Y1. Then Y2 and Y1 is defined, the joint PDF is only defined inside this triangle here. And so you have to be careful about the limit of integration. That is all that is really tricky about this problem. Okay, in any case, you want to integrate Y1 less than 0.5, Y2 bigger than 0.25. So we write out the integral from 0 to 0.5 and from 0.25 to 1 for the joint PDF. But the joint PDF is only defined based on this triangle. So because we have Y2 less than or equal to Y1, therefore the integral here for Y2 only goes from 0.25 to Y1. That's why Y2 less than Y1. Y1 now can go from anywhere from, but now because Y1 is bigger than Y2, and we assume that Y2 is bigger than 0.25, so Y1 can only go from 0.25 to 0.5. So as you can see, the limit of integrals between these two integrals changes. Here's 0.0, here's 0.25, and here is 1, and here is Y1. But in any case, once you know how to set up the limit of integral, then it's all simply integration of 3y1, and that is a simple exercise in integration. And so you get 5 over 128. So as I said before, the only thing that is interesting about this problem is that we have to be careful about the limits of integration. Okay, so we have discussed bivariate for discrete and continuous, and it is straightforward to generalize those definitions to the case of multivariate. And so in the case of discrete, then we will just require the vector x, the random vector of x, to have m components, x1, x2 up to xm, where each of the xi are discrete random variables. Then we will say that x is a discrete multivariate, and then we will define the joint PMF to be simply what we have here. So that's just definition chasing. And once again, for any subset A of Rm, the property of the set A is the sum of the PMF, the sum of the joint PMF. And once again, to avoid summation of uncountable elements, we will have to require this sum to be over all x for which px is bigger than 0. And this is well defined because the set for which the PMF is bigger than 0 is a discrete set. So this is summable. In the case of the multivariate continuous, then basically we're just required that the joint CDF, which is given here, can then be written as a multiple integral from negative infinity to x1 for z1, negative infinity to x2 for z2, and all the way to negative infinity to xm for zm. Well, technically speaking, you would rather write it as dzm dz1, because really you have to integrate from inside to outside, but that is, we don't do that just because there will be more things to keep track of. So you have to understand me when I say that you will know the limit of integration from the context. But in any case, now for any set A that's in Rm, for which A is now a countable union of hyperrectangles, so we write that as A is, say, like the union of rectangles, say, I from 1 up to possibly infinity of Ri, where the rectangle Ri, the hyperrectangle, is now Ai, Bi, multiplied by Cartesian product, we say Ci, Di, Cartesian product, we say like Ei, Fi, Cartesian product with all the way up to the rectangle for the interval for xm. Well, I guess to be more accurate, we should fix this notation wise. So we will write this as Ri as, say, like Ai1 to Bi1 product with Ai2, Bi2 product all the way up to Aim and Bim. But you get what I mean. Okay, in any case, for the kind of set, the property of that set is now written as the integral of a bunch of variables. So this all look messy, but luckily enough, note, we rarely, if ever, need to compute the probability of an event for general multivariate random variable by explicitly summing or integrating over set. In practice, nobody ever integrates multivariable integral, except in very, very special cases. So rather, for multivariate random variable, most of the time, we will find the probability calculations by simplifying, transforming the multivariate random variable to something else simpler, such as simplifying it to be a function of a collection of independent random variables. And we will make this clearer in the examples later in this class. So the main thing is that this definition here looks messy, but in practice, we never need to use them. So we never need to go past, say, like 2. And if you're very unlucky, maybe 3 variables. Okay, so we'll next define the notion of the marginal probability. So extending this definition, we will first define it for bivariate random variable. We will not define it for multivariate random variable, just that extending the definition is straightforward. So we shall not worry too much about it. In any case, if we have a discrete bivariate random variable x with a joint PMF p x1, x2, then we can define the marginal PMF of x1 to be just simply the summation of the joint PMF, sum of joint PMF with respect to the second argument. And similarly, the marginal for x2 is the sum of the joint PMF with respect to the first argument. Here. So in both cases, we have to be a little bit careful and just sum it over the pair for which the PMF is positive. Once again, avoiding summation of uncountable things. So in the case of a continuous bivariate random variable, instead of having marginal PMF, we have marginal PDF. So if you have a continuous bivariate that has a joint PDF, denoted as little f here, then the marginal is obtained by integration over the second argument. So the marginal for the first, this is the marginal of x1, is defined by integrating the joint PDF with respect to the second variable. And the marginal for x2 is defined by integrating the joint PDF with respect to the first argument. So once again, the marginal PDF are not probabilities. So just to reiterate the obvious, but sometimes we forget. So f1 x1 is not the same as a probability that x1 equal to x1, because that probability is always 0 for our x1. Rather, once again, similar to the continuous random variable case, the probability that x1 in some interval or in some set A, which is a union of interval, can be written as the integration over that set of the marginal PDF. So this is once again reducing it down to the same probability calculation as in the univariate random variable case. So a few examples. If we roll a fair die twice, then we recall that the joint PMF is Px1, x2 is equal to 1 over 36. So in that case, the marginal for x1 is just the summation of these 1 over 36 values 6 times. So that is just 1 over 6. And similarly for x2. In the setting tossing of fair coin 6 times, with x1 and x2 being the number of heads and tail, then we record that P of x1, x2 is equal to 6 x1, 2 minus 6. And so the marginal PMF is still the same as the joint PMF. Why? And the answer is simply that because the x1 and x2 in this case belongs to the set either 0, 6, 1, 5, 2, 4, up to 6, 0. So that means there is only one value of x2 for each value of x1. There's only at most one value of x2 for each value of x1 with Px1, x2 bigger than 0. So that is why the marginal PMF is the same as the joint PMF. Okay, so another example, which is a very useful example to remember. So you have a group of 3 Republicans, 2 Democrats, and 2 independent. And now you choose 2 people randomly to form a committee. So you let Y1 and Y2 be the number of Republicans and Democrats on the committee. And you want to find the joint PMF for Y and the marginal PMF for Y1 and Y2. So the joint PMF for Y is simply something that looks like a hypergeometric, but it's not exactly. But in any case, you can choose the Republican in 3 to Y1 way, the Democrat in 2 to Y2 ways, and then among the remaining 2 independent, you can choose the remaining committee member. assuming that y1 plus y2 is less than or equal to 1. So in that case, we have this as the joint PMF. So the joint PMF, you can write it out, will look like a table like here. And so the marginal PMF, whenever you have a table like this, in the bivariate case, then the marginal PMF are nothing more than the row sums or the column sums. So this is just a good observation to remember. A good way to organize your, say, your probability calculation. So in this case, the marginal for P1 is the column sum. You sum up this one to get 10 over 21. And the marginal for P2 are the row sums. And so you sum up the rows. So as another example, suppose you have x1, x2, continuous bivariate, and with joint PDF of this form. So once again, the joint PDF here looks as follows. Once again, you have the rectangle from 0 to 1. And then you say that you want to say x1 plus x2 is less than or equal to 1. So the rectangle goes from 0 to say 1. And x1 plus x2 less than or equal to 1. So what that means is that this here is 0 from 0 to 1, and you want to sum up everything to be less than or equal to 1. So the area of integration, if, okay, I see, I messed it up. It has to look like this. It is given by this triangle. So the joint PDF is defined on this triangle right here. This is the line x1 plus x2 equal to 1. So in that case, we just have to be a little bit careful with the marginal PDF, because we have to just once again be careful of the limit of integration. So the marginal PDF of x1 is defined by writing this integral out, but due to the limits of integration, the x2 has to be less than or equal to 1 minus x1 due to this constraint here. So therefore x2 only goes from 0 to 1 minus x1. And so if you do this integration, you get out simply this as the marginal PDF for x1, and the same, or just by symmetry, this marginal PDF for x2. So once again, for many kind of this kind of problem, you just have to be careful of the limits of integration. So it's maybe pays dividend to draw out the region of the definition for the joint PDF. Okay. And then one last example. So we now have a continuous bivariate random variable with the joint PDF of this form. And so verify that for any C in 02, fix C in 02, that this integration x2 is equal to 1. So you may want to verify that at your leisure. But in any case, the marginal PDF for x1 and x2 is followed by straightforward integration. So for x1, you integrate with the second variable z. For x2, okay, I think I draw the wrong arrow. the arrow should be x2 should be z, and x1, x2 here should be z here, as you can see. So the main point is that if you evaluate it out, you see that the marginal PDF for x1 is a constant 1, and the marginal PDF for x2 is a constant 2. So this provides a very clear example that why both x1 and x2 are marginally uniform, the joint distribution is not uniform. So this is useful example to remember. When you have marginally uniform, that does not necessarily mean that the joint have to be uniform. Okay, so now we will move on and revisit the notion of conditional probability in the case of bivariate random variable. So we will note first that the conditional probability for discrete is easy, but it's a little bit more complicated when we talk about the continuous case. Okay, so let's talk about the notion for conditional probability for discrete random variable first. So we have x1, x2, discrete. Then the conditional PMF of x1 given x2 is simply the function p little x1 given little x2 that is given by the probability that x1 equal to x1, x2 equal to x2, divided by the probability that x2 equal to little x2. So that's just basically probability of x1 equal to little x1 given x2 equal to little x2 that we recall earlier. And by the definition, that's just the joint PMF divided by the marginal PMF. And this is well defined as long as the marginal PMF for x2 is bigger than 0. So that is all easy and good. So we will note that that previous definition implies a few obvious yet very important properties that will be useful when we go to the continuous case. So the first is that the property that capital X1 belongs to some set A, given that capital X2 is equal to some element X2, you can just obtain that by summing the PMF, sum the conditional PMF over all x1 for which the joint PMF is positive. Similarly, for any set B that is in R square, so for x1 and x2, then the probability that x1 and x2 belongs to B, you can write it as the summation over x1, summation over x1, x2 in B of the joint PMF, and due to the definition, the joint PMF is just a product of the conditional PMF and the marginal PMF. So we have that formula here. So where the summation is over all x1, x2 with the joint PMF equal to 0. So those are obvious. But why do we cite this obvious property? And we will come back to it in a moment. But let's take a quick and, I guess, interesting example. So this is problem 5.39 in your textbook. So if we have x1 is Poisson with great parameter lambda, and x2 is Poisson with great parameter mu, and they're independent, then x1 plus x2 is Poisson lambda plus mu. We have seen this in chapter 3. So now the conditional PMF of x1, given that the sum, which we denote is a random variable z, so the conditional PMF of x1, given the sum of the two random variables, we can write it as follows. So that is the conditional PMF. We write it as the conditional probability. And because x1 and x2 are independent, this is the PMF for x1. This is the PMF for x2. And because x1 plus x2 together is Poisson lambda plus mu, this is the PMF for the sum. And so if you now do some simple algebraic manipulation, we have E minus lambda, E minus mu, together you have E minus lambda plus mu, so that cancels out. And then now you have divided by z factorial in the numerator, so you move that up in the denominator, so that becomes z factorial. And then you have x1 factorial here in the denominator, z minus x1 factorial here in the denominator. And then finally, by that expression, we have x1 plus x2 equal to z. So we can write lambda plus mu to the x1 for the first part, and lambda plus mu for z minus x1 for the second part. So in summary, that's the PMF of a binomial with mean with number of trials is z, which is the sum of x1, x2, the sum of the value, and the success property is lambda over lambda plus mu. So conditioning on the sum, then the marginal of any Poisson component is binomial. So now let's go back to defining the conditional PDF or conditional probability for continuous random variable. And now we have a difficulty. The difficulty is because we cannot define the conditional probability of x1 equal to little x1 given that x2 equal to little x2, because that probability, this probability here of x2 equal to little x2 is always 0. So we cannot define it like this. This is ill-defined. So how should we interpret this conditional probability? Because as we see, if we define like this, it's ill-defined because both terms here, numerator and denominator, are all equal to 0. So how should we define this conditional probability? Well, let's go back to look at the discrete case. In the discrete case, as we see earlier, we have this expression here, where we write the probability as a sum of the conditional PMF multiplied by the marginal PMF. So that suggests that analogously, we should define this quantity to be any function that satisfies this probability, this property. So replace the sum by integration. You still have the marginal. Now you replace the marginal PDF with the marginal PMF. And so now you can just replace the conditional PMF with the conditional PDF to be any function that satisfies this property. So we use this as the property to define so that is what we meant by the definition here. So as you will see in your textbook, they would define it using what we will see later directly. But here we just want to give you the intuition about why we defined it the way we defined it in the textbook. So in any case, if we have a continuous bivariate random variable that has a joint PDF, then basically the conditional PDF is any function f x1 given x2 that satisfied the property here that we say earlier, where we use here f2 is the marginal PDF. So in summary, we know that P of x1, x2 belong to B is defined normally as f of x1, x2 d of x1, d of x2. And we want this to be equal to this. So that is our definition of what the conditional PDF is. Well, that is a definition that is not really that helpful. So let's see what we can do with this. So if we use that definition with b belonging to interval for x1, interval from minus infinity to z, and for x2 to be the real line, then we have that by integrating the marginal PDF of x1, that's just the CDF, the marginal CDF of x1. And because x2 belongs to R, surely, so we have this by our definition over there, where we use the set, where we define B to be this form. And so we have here is this integration go from minus infinity to z. So this integration from minus infinity to z. And so the term that is inside here, this second in the integral, should look like the integrand in the first term. So we should have this property. So the marginal PDF is given by integrating the joint PDF with respect to the second variable. And that should look like this integration up here. So that suggests that the conditional PDF can be defined as follows. As we see, fx1, x2, fx1 given x2 times fx2. So this is one possible definition for the conditional PDF. And so this definition turns out to be valid, as in, if we define it this way, then it does satisfy the condition star, which is this condition here. So note once again that one very important point that I want to make, there is no unique conditional PDF. Just like there is no unique joint PDF. So this is just one possible definition. And in general, it is what is called as, this definition is known as the canonical definition. So once again, summary, for continuous bivariate random variable, the conditional PDF is not the same as the conditional probability, because this conditional probability is ill-defined, just because probability of x2 equal to little x2 is equal to 0. Rather, this conditional PDF is any function that satisfies this property for all sets B. So what we meant is that the product of the function f here and the marginal should be the same as the joint PDF. So this choice here is a canonical choice. It's not a unique choice, but it's a widely used choice. So we will discuss one last example before we end for today. So let us talk about this example here, which is example 5.8 in your textbook. So once again, we have a PDF, we have a joint PDF where now the domain of integration is of this form. So you have to be really careful, but the domain now will look like this. So this is y1 divided by y2 from 0 to 2. This is the line y1 equal to y2. So this PDF here is non-zero in this region. Okay, so we are interested, so the problem asks for evaluate the probability that less than half a gallon will be sold, given that the machine contains 1.5 gallon at the start of the day. So y2 is assumed to be equal to 1.5. Okay, so first we're interested in the conditional PDF of y1 given y2. So we first have to find the marginal. So the marginal for y2. And the marginal for y2 is this integration here. Where now we have to be careful of the limit of integration because now y1 is less than y2. So it goes from 0 to y2. So the integrand here is with respect to the first argument, z. So we have to go from 0 to y2. And that's y2 over 2. So therefore, the conditional PDF, one version of it looks like 1 over y2. So your textbook then define the conditional probability to be the probability that y1 less than 0.5 given y2 equal to 1.5. So you just integrate the conditional PDF from 0 to 0.5, and you get that that's the same as, this is the same as integration from 0 to 0.5 of 1 over 1.5, because 1 over y2, dy1, and so that should be equal to 1/3. But this is wrong, and maybe wrong in quotation mark. So rather, it is not really wrong, but it's just that it is not exactly what it means. So it's not exactly what it means because the property of y2 equal to 1.5, just to reiterate obvious, is always equal to 0. So you can never really observe that. But what it really means here is that that conditional CDF really refers to the property that y1 is less than 0.5, given that y2 is in some small interval around 1.5. So this is where I have to just mention a few things. So technically speaking, this notion of conditional PDF is maybe a little bit confusing because you always have to remember that the probability of an event is always 0. But in reality, in practice, you can just do all this calculation and they will still mean something. So you can still give meaning to them. So maybe at the end of the day, you don't really have to worry about all of this. Is it really probably 0 or not? And just do the calculation willy-nilly, and at the end of the day, you can still give meaning to it. So like here, this is not really well defined, but at the end of the day, we can still give a meaning to what it means. Okay, so we'll end here for today. For the next lecture, we will talk about independent random variable. Until then, take care, and if you have any questions, please send me an email. Bye-bye.